Midwater said, like finite element modeling, you take a structure. There are some analytical solutions, so you can go to a handbook and then see what the stresses in a pipe or a plate are. But for more complicated structures, you need a computational tool in order to solve that structure and see what the stress distribution or the displacements inside that structure are. Finite element methods is the most common tool in order to solve those kind of problems. So what you do is that you take your structure, you split it into these elements, like small things where we are gonna start doing some mathematical things in order to get the displacement at the nodes. So this discretization is based on elements, which is the area, and the nodes, which are the vertices of that element. So for example, here you have a wheel of a car, then you discretize it, and then you can see the stresses inside that wheel. There are different types of elements, so you can have points, you can have bars, you can have beams, you can have triangles and quadrilaterals. So we are gonna focus on two-dimensional problems, so we are mostly gonna stay here. And in particular in fracture, this kind of elements that is called 8-noded quad is the most used in fracture problems. So we are gonna start focusing on this one that is called 8-noded quadrilateral elements. So you're gonna have a global numeration. So you're gonna have n amount of nodes, which goes from 1 to whatever number of these little points you have in your domain. But you're gonna have still a local numbering, which is gonna go from 1 to 8, because you're gonna have 8 nodes in every element. So whenever you request an output in Abaqus, it's gonna have that local numeration associated to it, okay? So if you request the displacements in an element, it's gonna give you the displacements with respect to this local numbering, okay? And you can have either linear or quadratic elements. Quadratic elements, as you can see, they have more nodes. So you have 8 nodes. So they have better accuracy, but they use more computational resources in order to solve. So you're gonna have a bigger system of equations, because everything in finite elements comes to solving a linear system of equations, which is k times u equals f. And then you're gonna solve that system of equations. So the more nodes you have, the more degrees of freedom you're gonna have to solve at the end. But you have a better accuracy in regards to the displacement and stress field that you obtain in the structure. If you go to the other side, linear elements, they have this, what is called integration points. They go from 9 to 4, and then you have 4 noded elements instead of 8. So it's less expensive to solve this one, but you lose some accuracy, okay? So for fracture, we want super high accuracy where we want to compute the stress field near the crack. So we use these kind of elements, which are 8-noded quads. And that's what we are gonna use today. And for the homework, I ask you specific to use these kind of elements as well. So this is our example. So I'm gonna take this beam, this cantilever beam that has a hole, and it has a pressure and then a point force here at the end. And we are gonna take this beam and we are gonna take it into Abaqus, compute the stresses, compute displacements, and then like report in some particular locations the stresses, which are things that I'm gonna ask you to do during the homework, okay? So in particular, I'm gonna ask for the stresses at this point 1 and at this point 2. The beam, so not ask you, like this is what we are gonna do today. And the beam is made of two materials. It's made of steel, so this left part, the lighter gray, is made of steel, and the right hand side is made of aluminum. So you're gonna have two materials, okay? And we have a pressure applied here to the right, and then a point load that is going in the negative y direction. So with that, I'm gonna go to Abaqus, okay? This is Windows now, okay? And during like my experience with Abaqus, you have to be very organized where your files are. Because yes, if you're doing one or two simulations, it's okay. You can be, you don't have to be organized. However, if you are gonna run several cases, or you are gonna do a convergence analysis of the stresses near the crack, you have to be very organized with your names, and where you are storing the files. So in the desktop, I have created a folder that is going to be called class 1, and that's where all my files are going to be stored, okay? So I'm going to call that one my work directory in Abaqus. So how do we access Abaqus? I just go to Windows, like the menu here, and I'm going to open the Abaqus CAE. I also have the student version, so the limitation of that student version is that the maximum amount of nodes that I can have is 1,000. So today we are only gonna run this problem up to 1,000 nodes, okay? But for the homework, you have to do problems that are close to 10,000 nodes. So for that, you are required to use the computers that we have in the engineering building in the second floor. Those are full Abaqus licenses, so you have to use those in order to solve that. So this is our welcome menu in Abaqus, and I always close this one. I like to do everything here from the menu. Are you able to see? Yes, it's better. So the first thing that I told you to do is to set your work directory. So I'm just gonna go here to File, set my work directory, and I'm gonna browse until I find that folder because I want all the files to be stored in that folder. So I'm gonna go here to Desktop and select class 1 as my working directory. Okay? So now everything that I create, like result files, input files, reports, or whatever I ask Abaqus to do is gonna be created in that folder. So the first thing that I have to do is to create the geometry of my part. Abaqus is very smart in the way that it put things in order. So whenever you are doing a finite element model, I always go from top to bottom. Like you follow every single step. Some of them you need them, some of them you don't. But if you want to have a good model, you have to cover everything from top to bottom. Okay? So the first thing that we are gonna do is that we are gonna create a part. Okay? And in part we are gonna define the geometry of the beam. So I double click there. You can name the part. I am gonna name it beam. And we are not gonna do 3D finite elements. We are gonna do 2D. Okay? If at some point you get lost, please stop me and then I can answer your questions. Here the only thing that you have to change is, and you don't have to, is this approximate size. So if we go to our beam, we can see that our beam is 5 by 1. So our approximate size is gonna be 5. I don't need anything more than that. So I'm gonna go here and let's say that my approximate size is, let's put 10. So we are safe. And then I click continue. Then we are into drawing mode. And then we are gonna start drawing the beam. I want my X and Y coordinate or reference axis to be here. So that's gonna be my 0 or my origin for this beam. And in Abaqus, this is my origin where the two like dashed lines meet. So I'm gonna go here into the different drawing tools that you have, and I'm gonna select rectangle. For rectangle, you can either click wherever, and then you can see in the upper left part the coordinates of that point, or you can type in here the two coordinates. I like typing because I don't like clicking with the mouse. So my initial coordinate is gonna be this one. So that's negative 0.5 and 0 in X. And this coordinate in here is gonna be 5, 0.5. Correct? Notice that Abaqus doesn't have units. You give Abaqus the units. So if all your measurements are gonna be meters, just be mindful that everything that you are doing is gonna be in meters. If you were to work in millimeters, everything is gonna be in millimeters, but Abaqus is unitless, okay? So my starting point is 0 in the X coordinate, comma, negative 0.5. And then my endpoint is gonna be 5, 0.5. And that's and then you scroll down with the, you zoom out with the scroller, with the scroll in the mouse, okay? So that's my beam, okay? What am I missing? So if we go here, I'm missing the circle. So let's do the circle. So the center is at 2,0, and it has a radius of 0.3. So I'm just gonna select the circle tool. My center is gonna be in 2,0, and my radius is gonna be in 2.3, 2.3, 0. I hit enter, and then I just finish drawing my circle. Okay. And I think that's for geometry. So I'm just gonna click the X in here. Yes.
Does it make any difference that if the lower corner, the lower left part is going to be a 0, 0, and we draw from that point, or the horizontal line will be at the center of the space?
It doesn't matter. Like, the only thing that is gonna change if you draw your beam here or here are the coordinates of your node. But the stresses and the solution of the displacements, everything is gonna be the same.
The way we force the solution, does it affect it?
It doesn't affect it. It only changes the input file, because now your node 1 is not gonna be here, but here. But in terms of the solution, it's gonna be the same.
When navigating across the plane, do you have to scroll out and scroll back in, or is there some shortcut key on the keyboard?
Like, if you wanna do this,
Yeah, instead of having to use a mouse, can you...
like, if you get lost at some point, then you can click this one, and it's gonna bring everything to the center.
Okay, but if you want to move left to right...
Okay, so for that, you have to hold Control and click the scroller, and then you can move. So for those of you that are familiar with SolidWorks, like I was, so this is what you do. You go to Tools, then you go to Customize. Oh no, it's in... Actually, I have to get outside of this menu to change that. So, okay, I finished my geometry, so I'm gonna say done, and then we created our geometry, okay? Now, because I asked for some stresses at some particular locations, which is this 0.1 and this 0.2, I'm gonna have to create something that is gonna be called partitions, right? So I'm just gonna define, like, I'm gonna scratch the surface, so whenever I create the mesh, it creates the mesh in that particular point. Because I'm gonna ask for the stresses at this particular location. So I'm just gonna like split the beam in two, so I can have a node at this point number 1. And the same thing for the node point number 2. So how do we do that? We go to this tool that is called partition face. So I select that one, and if you check, like, my origin is now moved. So I'm just gonna go to this part in here that is called Sketcher Options, and then I'm gonna say, hey, I'm gonna create a new origin, and this is gonna be my new origin. So I just went back to the way things were before input, like getting into this partition phase. So I'm gonna create the first partition. So it's gonna go from here to here. In that way, I created a point in here. So we want a point there, so we can later ask for stresses at that point. Then we do another one, which is this one, that starts at 4.2. So I'm just gonna create a vertical line at 4.2. So how do I do that? I just select the coordinates. So it's 4.2, comma, minus 0.5. And then I just go in a vertical way. Whenever you see the V, is that you're going vertical in Abaqus. But you might say, okay, you created a point in here and a point in here, but you didn't create the point at the middle. So what I'm gonna do is that I'm gonna split this line in two. How do I do that? Like this. So that's like the partitions that my experience tells me that I need in order to request the stresses at those particular points, which is gonna be 0.1 and 0.2. And that's it. It's the same beam, but it's not into these 3 different like partitions. Sorry, 4 different partitions. I think in terms of geometry, that's everything that I need for my beam. There's nothing else that I need. So you guys remember that I told you that you have to follow the steps from top to bottom. So the next step is that we are gonna create the materials. So double click in materials, and I'm gonna create my first material, which is gonna be the steel. We are gonna work under linear elastic conditions, so we don't have to define plasticity or yield stress or like damage. So there are a lot of like properties that you can define in here, but I'm just gonna cover the basis, which is gonna be like defining 2 things that are needed for linear elasticity, which is the elastic modulus and Poisson's ratio. Okay, so that's everything we need. So here on the mechanical tab, I'm just gonna go to elasticity and select elastic because our material is gonna be elastic. It's gonna be isotropic. You could do lamina, like for composites. You can do orthotropic, but we are gonna use an isotropic material. The Young modulus, if we check here for the steel, is 200 gigapascals. So there comes again like, what units should I use if Abaqus doesn't have units? So my units of stresses are gonna be in megapascals. So whatever stress Abaqus is gonna give me later is gonna be in megapascals. So my elastic modulus is gonna be in megapascals as well. So 200 gigapascals is 200,000 megapascals, correct? Or 200 E3. Abaqus also understands this. And the Poisson's ratio is 0.3. I click OK, and then I have a drop menu now under materials, and then I have steel as one material. I have to define the aluminum. So I'm just gonna create another material called aluminum. And again, mechanical, elasticity, elastic, and then my Jones modulus is, I think, 70 gigapascals, so that's 70 e to the 3, because I'm working in megapascals, 70 e to the 3, and my Poisson's ratio is again 0.3. And I'm gonna click OK. So I have materials. I can keep expanding the list as I want, but I only need 2 materials for this case. Then the next thing is to create a section. So create a section is that you are gonna have, it's an intermediate step. I don't really understand this one, but it's like an intermediate step that Abaqus needs to assign a material to a specific like partition of the geometry. So you have first to create the sections and then you assign them. So I'm gonna create this section that is gonna be called a steel section. It's gonna be homogeneous, and then it's gonna ask me, okay, what is the material associated with that section? I'm gonna say that my material is gonna be the steel, and we are working under either plane strain or plane stress formulation. So you can modify the thickness in here, but by default, it's assuming a 1 unit thickness. So we are gonna leave that like that. So I created the section for the steel. Let's do the same thing for the aluminum. So I'm just gonna create aluminum section. It's again homogeneous, but now the material associated with that one is gonna be the aluminum. Okay, so I created these 2 sections, and now I have to assign them. How do I assign that? I just go to that menu that is called assign section. If you forget about what everything does here in the Abaqus menu, you just leave the mouse over the icon and then it tells you what to do. So I'm just gonna assign the section, and the first one that I'm gonna do is gonna be the steel one. So I'm just gonna select this one, hold shift, and also select this one because that's the part that is done of steel, correct? Here Abaqus has like a question, hey, would you like to create a set? So like later, a set is whenever I'm requesting, for example, the stresses, I can tell Abaqus, hey, I'm only interested about the stresses on the steel. Please give me only the stresses of the steel. But for that, I will have to create a steel set. So yes, I'm interested in creating a set, and let's call it a steel set. Okay? And what is the section that I'm gonna use for these two red regions? It's gonna be the steel section. And then I click OK. By default, whenever Abaqus is green, it means that it has a material associated to that particular partition. Then I'm missing the other section, so I'm just gonna hold this two, and then I'm gonna say that is the aluminum set, because I want to create a set, and the section associated with that part is gonna be the aluminum section. So now everything is green. That means that everything has a material associated to it. I can now exit that menu and go to the next step. So we covered sections. We don't have profiles. Everything is a unit thickness. So whenever you are doing beams, you could have different profiles, like the eye profile or the square or the hollow square. So you can use those profiles that are predefined in Abaqus, but we don't need that in here. So the next step is called assembly. So Abaqus is expecting a lot of pieces. Like, for example, if you were modeling an engine, you would have tons and tons of pieces, right? In this particular example, our only piece is this beam. We don't have any other parts into our assembly. However, we need an assembly, okay? Which is made of only one part. So I'm just gonna open this drop menu, and then I'm gonna bring an instance. So that's Abaqus taking the geometry that we just created, the materials and everything that we just defined, and it's gonna bring it into the assembly so we can like compute stresses and everything for that beam. So I'm gonna double click in there, and always select independent, because with that you can like modify the mesh only on the instance, and you don't have to modify the part. So select independent, okay? I'm gonna click OK, and now I'm working on the instance. So let's see what other options do we have here into the assembly mode. We have position constraints. We don't need any of that. Features, that's this coordinate axis. And then we have sets. You remember that when I was defining the materials, I created the sets. So you can, if you click on that one, you can see the sets that are associated, like where the sets are. Whenever I'm gonna define the boundary conditions, that means that, for example, in this right edge, I'm gonna apply a pressure. I'm gonna have to apply the pressure over that edge. I could create the set that is gonna have like that boundary condition associated to it. So I can either do it in here or when I'm doing the definition of the boundary condition. I like to do it when I'm defining the boundary condition, but you can also do it in here.
For position constraints, that's not the boundary condition on.
No, it's like if you have multiple pieces and then you need these two holes to be aligned, that's a constraint. Okay, but we don't have any constraints because this is our only piece. Okay, and here in engineering features, if I open this menu, is where we are gonna have cracks, which is something that we are gonna use in the part 2 of this computational aspect of fracture mechanics. But it's just so you know that cracks are defined in the assembly mode. So we don't need anything else from the assembly. Okay, and then I'm gonna go to the next step, that is a step. I have to define what is the kind of physics that I'm trying to model or recreate from real life into my computer. So you can either do a thermal analysis, you can do mass diffusion, you can do electrostatic analysis, thermoelastic. But for us, we are only gonna do a linear elastic, or what we call, or how it's called in Abaqus, a static analysis, which is only pulling and applying some loads and displacement boundary conditions into my beam. So I'm just gonna double click in here, and Abaqus has already an initial step, which is like your beam in your natural state, like nothing is being applied to it, everything is without forces. Or you could define, hey, initially my beam has some temperatures. So that I could define that in my initial step, I have a temperature distribution. So then my stresses are gonna be affected by that thermal distribution. But for now, I'm not gonna modify the initial step, and I'm gonna create my second step that is gonna be static and general, and I'm gonna call that one applied load, because that's what we are doing. The beam was in rest position, and then we are gonna apply some loads and displacement boundary conditions. Here's like some things that you don't have to modify, like for the purpose of this class. But if you had nonlinear geometry, that means that your displacements are too big, then you will turn this one on. But we don't need that one. We are working under small strains, okay? Incrementation, that's whenever you're doing a nonlinear analysis. So you have a curve, and then you have to do linear steps in order for your solution to converge. And then others is like the solution method that you're gonna use, if your stiffness matrix is gonna be stored in a symmetric or unsymmetric way, what is the solution technique that we are gonna use, and some extra stuff that some of you guys, if are interested in numerical techniques, you can start like checking whatever is in here. But we don't have to modify anything in here, so I'm just gonna click OK. If I open this step menu, then I see that I created a step that is called apply load. I'm gonna open that apply load menu, and I'm gonna define my loads and boundary conditions. So all the things that I'm doing into that, like whenever I'm pulling the beam and applying that boundary condition. So the first thing that I'm gonna do is to apply the loads. So I'm just gonna double click in here, and I'm gonna apply the pressure at the right end, okay? I'm just applying a stress, which is a pressure. So let's call this one pressure. So what kind of force I'm creating? Is a pressure, correct? In which step I'm gonna apply the pressure? In my apply load step, correct? So I'm just gonna click continue, and then Abaqus is gonna ask me, select the surfaces for the load. So I'm just gonna select this right edge, and with shift, I'm gonna select the other edge. So now these two edges are where my pressure is gonna be applied. Do I want to create a surface? Yes, it doesn't hurt. So I'm just gonna call that one right surface. Okay? And now it's gonna ask me what is the magnitude of the pressure. So you remember that we were working in megapascals, and the pressure that we need to apply is 100 megapascals. So I'm just gonna put 100 here. Is a positive pressure in the negative x or in the negative y direction? Sorry, negative x or in the positive x direction. So pressure has to go inside the surface, right? So if we are trying to pull, we have to apply a negative pressure. So then we have to do negative 100 in here. So we have the pressure going outwards of the surface. Okay, so be careful of that. Then I'm gonna apply another pressure that is gonna be my point load. So I'm just gonna call this one concentrated force. And it's gonna be a concentrated force. So whenever you apply a concentrated force, it's at a node or a point. So I'm gonna apply the load in here, in that point. Okay, so now, if in the homework I ask you to put a load in here, you have to do what? A partition, and then create a line so you can have later a load defined at that particular point, okay? So I'm just gonna click OK, and my concentrated force is only vertical. So 1 means the x direction, and 2 means the y direction. So in x, I don't have any force, and in y, it's gonna be -1, because I'm gonna keep working in kilonewtons. So my applied load is -1 kilonewton. Okay? So I'm just gonna say okay, and then I have my applied load or concentrated force at that particular location.
You said that you created a surface when you applied the pressure?
Yes.
And is it the same if we don't?
Yes. So the only thing that with creating surfaces is that later, when you are requesting outputs, you can request an output for that surface only. Okay? So
But if you don't create a partition at that edge, could you just create a surface and that'd be the same thing? Or
this partition here,
yeah.
yeah, you don't have to create a partition because whenever I apply the load in here, I have to select both edges. So I could have split this line in two, but that's more a complicated process. So I didn't have this partition in here. But yes, you don't have to create a partition in order to apply that constant pressure. Was that your question? Okay.
So then if we have a node on the top surface, we can just split the line without partitioning and place the load there.
Yes.
And it's done in the stretch part, in the sketch part?
In the sketch, and you can also do the partitions in here. Right, so the partitions that I did, and that's a very good question, were created in the part. So whenever I bring the instance into the assembly mode, it's gonna have those partitions. But now, if I only want to create the partitions into the assembly mode and not modify my base geometry, I can do the partition in here.
So you leave the original untouched and you just...
But it's the same process. It's just where your partitions are created, but it's the same process of creating those. So that's loads. I don't have any other loads in here, so I'm just gonna apply that displacement boundary condition in here. So I'm just gonna restrict the X and Y displacement at that end. That's not the best way to do it because your beam is gonna be stretched and that's gonna create like a fake stress, like right there at the left end, but that's the way that we are gonna do it today. So what's the name of that boundary condition? Let's call it fixed end. And it's going to be a displacement boundary condition, and it's going to be applied in this step that is called apply step. So where do I have to apply that boundary condition? Right here at the left edge. So I just select it, and I'm going to name it left edge in case I have to request any particular output later in that left edge. So I always create sets. It doesn't hurt, like if you don't have to redo everything again if you are interested in a particular, like for example, a stress or reaction force in a node that is lying on this edge. So I say done, okay? And now I'm gonna fix the X and Y displacements, and they are with a value of 0. That means that I'm gonna restrict that movement in there. So that's it. I have a fixed end, I have an applied load at the end, and then I have a point load at this top right point of my beam. Then, before meshing, I like to think about the requests or outputs that I'm gonna need from my analysis. So for now, I'm only gonna ask about stresses, strains, displacements, but later, whenever we go into cracks, we are gonna have to request the energy release rate and other types of energy for our analysis, and then we understand what's going on with the structures. So for now, Abaqus has by default created like a default field output. So if you double click in there, those are the outputs that you are gonna compute, or like the output quantities that you are gonna compute after you compute the displacements. Everything is computed from the displacements. So you're gonna compute stresses, strains, displacements, forces, contact. We don't need anything contact. We could ask about energy, like the total energy of the structure. And I think that's everything that we need. And it's gonna do that for the whole model. So you remember, like maybe I have a part that I'm not interested in, so I could say, hey, I'm only interested in a set, and that set is called beam steel set. So it's only the steel part. So Abaqus is not gonna compute anything for the aluminum part. But I think we are interested in everything, so I'm just gonna ask for the output quantities for the whole model, okay? And then I'm gonna say, okay, those are my output requests for this one. I'm not gonna go through the history output request. That's more for nonlinear analysis and when you are computing fractured quantities. So those are gonna be covered in the next session, okay? Then I keep browsing from top to bottom. I don't need any interactions, properties. I don't need contact. I don't need any constraint. I don't have fields. I don't have, this is more like for nonlinear analysis. And then if you open this load and boundary conditions menu, you can see that I have my concentrated force and pressure already created there. So you can either create them here inside the step definition, or you can define them in here in this left tree, also right there at the bottom. So the only thing that we are missing is mesh, okay? And this is a very important part. I'm gonna spend some time in that because meshing and the way you mesh in fracture problems is very important, okay? So how do I go into the meshing module? You have different modules in here, and then I'm gonna go to mesh, okay?
Why did you say history output is for nonlinear method?
So for example, in history output, you are gonna request the displacements at a particular node for every time increment, so that's more in nonlinear. So like everything that I'm gonna request in this part number 1 is done using a field output request. If you request energies or contact or fractured energies, then you need a history output request, but we don't need those for this example. Because in history output, if you have a nonlinear behavior, then you ask for every time increment and for every element and for every node this output quantity. So it becomes very...
So doesn't field output do that?
Yes.
It does do that. So
Yes, but we are in a linear increment, so it's going to be only computed at the end of the linear increment. So I'm going to go into the mesh module. And in mesh, the first thing that we have to do is to define our element type, okay? So that is done here in this SIR menu. I don't know why it's called like that. So I'm just gonna click there, and I'm gonna use the same element for my entire part. So I'm just gonna select everything. I say done, that's my selection. And then I'm gonna browse here until I find plane strain. We are gonna use a plane strain formulation. So plane strain, quadratic. So you remember the difference between quadratic and linear elements. So this is the one that we are gonna use. So let's select quadratic, and I want full integration. It's gonna take more time to solve, but my answer is gonna be way better, okay? So I'm just gonna select full integration. And here's the name that Abaqus has given to that element type, which is CPE8, okay? So I'm just gonna say okay, and that's my element type for my entire mesh. Then I'm gonna define some mesh controls. So sometimes Abaqus likes to create triangles. Whenever you have like holes or you have a crack, it likes to create triangles instead of quadrilaterals. So what I'm gonna do is that I'm gonna be sure that Abaqus creates quadrilateral elements for my entire mesh. How do I do that? I select again my entire mesh, and then I'm gonna set quad. Please don't select quad dominated, because quad dominated is says like, okay, my main element type is quadrilateral, but if your meshing algorithm thinks that a triangle fits better this part, it's gonna create a triangle. But I don't want that, okay? I want quadrilaterals everywhere in my mesh.
It changes to triangle automatically?
Yes. So sometimes you create a beautiful mesh, you spend a half an hour creating the mesh, then you submit the job, and then it says, hey, you have quadrilateral and triangular elements, Abaqus cannot compute the J integral or your energy release rate. So just this is like a double check to ensure that your element type is only quads.
So is it ever beneficial to have the quad and the triangle mixed together, or?
It's less computational resources, but for fracture, we can mix elements. It has to be all quadrilateral. So any time that I do a finite element simulation, I only use quadrilaterals. And how it's gonna solve, or like what is the meshing algorithm, I'm just gonna say, hey, create a mesh in a free way. So if you were to have a perfect square without circles in the middle, it will create a structured mesh, right? But then if I say, yes, go ahead and create the structure mesh, it's gonna say, hey, but you have a hole in here, I won't be able to create a beautiful square mesh. So I'm just gonna say mesh in a free way, okay? You can play with the different meshing techniques, so you can try different algorithms. So for example, you can say, in this part, I want a different algorithm. So for example, in this part, sorry, like let's assign a different meshing algorithm to this part. Let's use medial axis structure. I don't know what that's gonna create, but you're gonna tell the difference between the two parts. And again, let's make sure that everything is that everything is quad. Okay, so everything is quad, so we are good to go. And then sometimes for cracks, you need a good refinement near the crack because you want your stresses to be super accurate. So the more nodes you have, the better your solution is gonna be, but the more computational resources you're gonna have. So you have to start playing, how many nodes do I want, but how much time do I want to spend running this simulation? So what I like to do is then I like to create a general seed. Seed is like a partition that Abaqus is gonna create on the edges, and then from there is gonna create like the mesh. So if I go here to seeds, it's gonna give me like, okay, your element seed size is gonna be 0.2. So that means that in an edge that is 1 millimeter is gonna have, 1 meter is gonna have five elements because it's a 0.2 size. So if I apply that, that's how my like edges are gonna be discretized. That might be too coarse, like my mesh is not refined enough. So I could change that from to 0.1. That looks better, okay? So I could say, yes, I think that seed is good enough. But I could have parts in my mesh that need more refinement, correct? So that you do it with this menu that is called seed a particular edge. So I'm just gonna select this one. I'm gonna say, hey, this region of the circle is crucial for my simulation and I need a good stress distribution over there. Go ahead and refine it. And let's say that I want to refine it by number. So it's the number of like partitions that the edge is gonna have. So let's say that it has a big number, I don't know, 40. Okay. So you can see that how the partition is gonna look like for that section of the circle. So it's gonna have a super refined mesh in there. How do I mesh the part? I just go here and I select mesh part instance. There's something curious about Abaqus is that, can you guys see the little arrow right here at the right edge? If you hold this button, you're gonna have 4 extra options. Okay, so that's more like useful in the meshing technique. So for example, you can mesh a particular region, you can delete the mesh, or you can delete a particular region of the mesh. Because when you have partitions, as we have, you can start meshing by parts and see that you like the mesh for every part. So let's do that. Let's create the mesh for only a region. So what region do you want to be meshed? Let's say that this one. And then I'm gonna click OK. So that's my mesh. Okay. You can see that I have a super refined mesh near the circle. Now, okay, I think that I don't care about how the mesh is gonna look like for the rest of the beam. Let's mesh everything. So I'm just gonna hold that button until I see the 4 options and then say mesh everything. It's gonna ask you, is it okay to mesh everything? I'm gonna say yes. And then I created everything for the mesh. You can tell that it has two different meshing algorithms for this left and for this right part. So you can play and see which mesh you like it better. Okay. Now, because I'm running Abaqus student version, I think that I have more than 1,000 nodes. Let's check. Okay. So I'm just gonna give you another tool that is query. I think that's how it's called. So I'm just gonna go here to tools. I'm gonna query, and I'm gonna inquiry Abaqus about my mesh. And I'm gonna say, give me all the information that you have about that mesh. So here, you can tell that it has 2,219 nodes with 683 elements, and all of them are CPE8. Okay, so that's more refinement that the one that the Abaqus student version can handle. So what I'm gonna do is that I'm gonna delete this seed over here, because I think that the local seeds that I created in this section of the circle are too small. So how do I do that? I just hold this one until I see this eraser, and then I'm gonna say delete the seeds that I created on that edge. So I just do that, and then it says, if you do that, I'm gonna have to delete the mesh. Okay, that's fine. Go ahead and do it. Okay, and let's mesh the part again, but only with the global seeds that I created before. Is it okay to mesh? Yes. Let's check the number of nodes. Query, mesh, the entire assembly, or you can only instances of regions. You can query different parts, but I'm gonna query the entire assembly. And now it has 16,000 nodes. That's too high. So I'm just gonna reduce my mesh size to 0.16. Delete the mesh, and let's mesh again. Let's tools, query, mesh, and now it has 719 nodes. I know that it doesn't look that you're gonna get a super good accuracy in this one, but we just want to run and then post-process the results, okay? Even if our answer is not gonna be alright. And that is something that you guys, that I ask you to do during the homework. You're gonna try 4 or 5 different mesh densities. How refined your mesh is that is called mesh density, so going from 100 to 10,000 elements. And then you're gonna see how your solution is gonna converge when you increase the number of elements. So that's something that you're gonna have also to study during the homework. So I'm happy with my mesh. The only missing part is to submit the job. So I'm just gonna go here to job. That's the only part. I don't need predefined fields, remeshing, sketches. I don't need anything else from this menu. So I'm just gonna double click here and just gonna say create a job. The job is from that model 1, because you can see that everything is under the name model 1. And how am I gonna name that job? The sim beam analysis. Okay. Here's about memory usage. If you have multiple cores, like how you can parallelize that. If you want more or less cores. If you want your solution to be with single or double precision. Double precision is gonna give you more decimals, but it's gonna take way more time than the regular one. So I'm just gonna leave it in single. And I created the job, but I didn't submit it. How do I submit the job? I just go here to job manager and say, hey, this beam analysis job that I just created, I want to submit it, and I want you to solve the system of equations because I want to see the results and how this beam deforms when I apply these loads. So I'm just gonna submit the job. We are gonna check here. So the job has been submitted for analysis. It read the file and it already ran. Okay, so we already have a solution. Let's check the solution. So I'm just gonna go here to job, and I'm gonna select the job that say that has been completed. Right click, right click, and then I'm gonna check the results of that job. By default, it's gonna show you that. Let's see how that is called. Plot on the form shape. But then we all want to see the beautiful colors and the finite element colors that everyone likes. So I'm just gonna click on this one that is called plot deformed configuration, or plot contours on deformed shape. So that's how my beam is gonna be deformed. The deformation is scaled. This is not how it really looks, but it gives you a behavior on where is like the highest and the lowest stresses in your part. As you can expect, because of the presence of a hole, we are gonna have some stress intensity some stress concentration near the hole. Where is that concentration? Is right here. Okay. What the magnitude of that concentration is this one. Okay. You can have different, so I'm just gonna browse through those menus. So S means stresses, and here is what stress you want to be like shown in your screen. So for me it says S11 means the stress in the X plane going towards the X direction. So that's the stress 11. Sigma 22 is the stress in the Y direction coming from the Y plane. So that's sigma 22. And then you have sigma 33 because we are in plane strain, no plane stress. Then here you're gonna see all the quantities that you requested in your field output request. So for example, we can have the displacements. So you can have the magnitude or what the displacement in X is. So as you can imagine, you have a greater displacement here towards the end, whereas here in the end, your displacement goes to 0 because of the boundary conditions that we applied in here.
Is this the result of field output?
Yes.
So if we don't select like displacement in field output, we won't get this visualization.
If you don't select displacements in the field output, you won't get this.
So,
but those are by default in Abaqus. The only way of not requesting those is like messing around the way I did. Like because I didn't create a new field output, but I just modified the one that Abaqus has.
If we had a nonlinear material, we would only see the visualization of like the linear part.
No, you will see the.
You said we only use the field output.
But history output is more like for a particular set. So for example, if you have a crack, for every time increment, you're gonna ask Abaqus to compute the strain energy release rate for the crack, and that requires a lot of computation. So if you don't tell Abaqus in your output request, history output request, to compute those quantities, you are not gonna do them. But the base one, which are the displacements and strains and stresses, yes, they are gonna be computed for everyone.
The thing you're saying is that we use the field output to get just the nice visualization.
For every time increment. But in linear increment, you only see it once. Output history output request, I only use it for cracks. To get the energy graph, correct.
So if you had done your time steps and you're doing plasticity, so you actually.
So one output request that you can have in plasticity is like the amount of yielding, which is not a normal request, but you can say, hey, for every time increment, show me the elements that are yielding and the ones that are not. So Abaqus is gonna go ahead and look for all the elements, see which ones are yielding, and then give you all of those into the history output request. But it's some specific energy quantities and scalars, or if you have damage. So for example, hey, I want for this particular element damage like history. That's why it's called the history output request. So from time step 0 all the way until the end of your simulation, show me how the damage in that element evolves. Okay.
Would that be something you access through the drop-down menu, or is that something you can export?
No, you like if you go here to model, then you can say, hey, here in history output, you can give me failure. So for example, damage. Then you have a stiffness degradation for cohesive elements. But those are more complicated stuff. So for example, when you have contact, you can ask for like the reaction force between the two things that are in contact, but that's done in a history output. I just see them like two different things, like basic stuff and complicated stuff that is not a a regular thing.
And you requested for the field output for first, second, and last, correct? For the last.
For the only when you have a solution for the, because in the first increment everything is 0.
0. You requested for only 0 and last.
No, only for the last
Only for
step
the last
because
one.
this is a linear
So you don't
increment.
have the visualization for the middle of it.
No,
You don't have.
only
Even
when
if
you
you-
apply the entire load, because if I want something in between, then I have to split my linear increment into 2 linear increments. So I have a solution in the middle. But
So
I'm
the
only
step-
solving the system of equations once.
So you define your step for only one.
Correct. Correct. It's only one increment.
So do we have element local orientation here? So if it's S11, we meant that it would be on the plane of 1 in direction of x.
Correct.
How do you know which direction plane of 1 is?
The same as your base coordinates.
It's global.
It's global.
So it's not local.
It's not local. What is local is your element numbering. And for example, if you request the stresses at element, it's gonna give you the stress as the integration point 1, 2, 3, 4, 5, 6, 7, 8. So that's when this local numbering comes into place. Because if you have the stresses at the node 1 of the element 5000, it's gonna give you the displacements here. But it doesn't matter how deformed your element is, your S11 is gonna be the same for all the elements. It's gonna be x and in the x direction. So I'm gonna go again into results. So I'm gonna open again the results. So right click and then results. And I'm gonna check this point, right? Because I need the stresses at this particular location. So I can either do it 2 ways. I could have created a set previously and only ask for the stresses for that set, which in this case is only 1 point, or just ask for the stresses everywhere and then see what this node number is, okay? So I'm just gonna go here to tools, query, and I'm gonna say, I'm gonna query a node. And the node that I'm gonna query is this one. So it's saying that the node number is node number 8. So if I want the stresses, I'm just gonna request the stresses for all the part, for my entire domain, and see what the stresses in node number 8 are, okay? How do I do that? I'm just gonna go here to report. And I'm gonna report a field output. And by default, the stresses are computed at the integration points. So you have stresses information only in these green points. But Abaqus has a nice subroutine that extrapolates the stresses from those 9 points to each element, to each node of the domain. So if I ask you for stresses at integration points, it's a different answer than if I ask you for stresses at a node. You can also ask for the average stress at an element, so you can have like a sensation of how loaded or how stressed that element is by computing the average, or the von Mises stress for everyone and then computing the average of the von Mises stress for the element and things like that, okay? So I'm just gonna say, I want the stresses, and go ahead and give me von Mises, sigma 11, sigma 22, and sigma 33, and sigma 12. Give me all of them. But I don't want them at the integration point, just give them at the nodes. So I don't know why it's called like that, but they call it unique nodal. So just take those stresses from the integration point and extrapolate them to the nodes. So that's it. Only give me those ones. And then I go here to set up. So
if you use integration point, how do you understand which point it is?
So that's when the local numbering comes in. So you're gonna have stresses for integration point 1, and then you have 4 stresses, or whatever stresses you requested. Then for integration point 2, then for integration point 3.
So the number is fixed. You have to
Yes, let's do both. Okay, so I'm just gonna ask for the stresses at a node, and then I'm gonna show the stresses at the integration point. Okay, so I'm gonna go here to setup, and then I'm gonna rename the file that I'm just about to create. I'm gonna create them, call it as nodal stresses.txt. You have to give Abaqus the format. You can start messing with how your output is gonna be written into the text file. So I want 9 significant figures, and then if you like scientific notation or engineering format, that's up to you. And I'm just gonna click OK. So where is gonna be the file written is gonna be here into my working directory. So I'm just gonna open this one, nodal stresses, and then you see that for every node, it's gonna give me the 4 stresses, which are computed using weights and integration, and then taking all the 9 integration points and computing an average, and then a quadratic interpolation scheme, and then it computes the stresses at a node. So it's a fairly complicated routine, but Abaqus does it for you. Okay, so then if in the homework, which I did, I ask you for the stress sigma to 2 at node 8. So I'm just gonna go here. At node 8, and then I'm gonna check the value of sigma to 2, which is negative 8.93. So that's 8 megapascals. Okay?
We have 700 nodes.
Yes.
What does it mean at location 1?
Where
So it's like S11
S11 is the stress.
at LOC1.
Check out the columns.
That's I don't know. I mean, when we like in a second when we compute the stresses at the integration point, you're gonna see different locations because you have actually 9 locations.
That's why it's 1.
Mm-hmm. It's only at the node.
Ah,
Yeah, thank you for the question. So let's go ahead and create a new field report, but now at the integration points. So I'm just gonna go here to report a field output, and now at the integration point, and I'm only gonna select 2 stresses, sigma 11 and sigma 22, so it doesn't get very messy. And the setup, be careful. You have to change the file name, or otherwise it's gonna append to the file that you just created before. So I'm just gonna call this one integration point stresses. And then if I go here and open this one, okay, so location 1, I don't,
We still have that.
yes, but then you have for every element, so you can see that how many ones do I have in there? I have 1, 2, 3, 4, 5, 6, 7, 8, 9. That's for every integration point. So for my element 1, I have 9 integration points, and in every integration point, those are the stresses. So that's when the local numbering comes into place. So you have the stress 1, 1, and 2, 2 for this point, the stress 1, 1, and 2, 2 for this point, and so on for the 9 integration points. If we choose reduce integration, we are not going to have 9, but we are going to have 4 integration points. But your stress field is going to be only based on 4 points, so it's going to be less accurate. And remember that for fracture, we want a high accuracy when we are computing the stresses near the crack. You have a question, right? No?
so we have, if you want to get the average, it's the same as having the 9th one in the middle. If we go to the previous slide that you had.
I think so.
So you have 9 integration points. If you request the average should be the one in the middle, right?
So let's do that. Report, field output. So actually that one, result, history output. Let's check what the history output requests are. I don't know if I asked for that one. Whole element.
Shouldn't this set
Centroid. Yes, the stress as a centroid. So it's only the stress at the center of the element.
Does it use the average of the points, node points too, or only the integration point?
Only the integration points, because the stresses are only at the integration points. When you have stresses at a node, it's because you did a weighted solution in order to extrapolate for the node. So stresses are at the nodes, and stresses integration points same as strains, but displacements are computed at the nodes. Yes, you don't get displacements at the integration points.
Or you also don't get stresses at the,
Stresses inside the element and nodes have displacements.
You have stresses at the nodes, but they're extrapolated.
They are extrapolated from whatever you got inside.
Right.
Okay.
Daniel, I know there's a class coming in after this. So.
I think that's it. And regarding if you have questions about this, I'm thinking about after Tuesday class, I'm gonna stay here for a while in case you have questions, and I'm gonna bring my laptop. Oh yes, I'm gonna be outside, and then we can go to the conference room in the AT building in case you would have questions regarding modeling or the homework. And if you think that is something that I can manage through email, go ahead and write an email. But if not, I will either not respond or just say, let's meet after class. Okay? And that's it. And the homework is already uploaded to Blackboard, and then start working as soon as possible in the homework so you don't have questions before the submission.
Yeah, so Daniel, I'd be happy to help with questions and comments if there's more than simple questions.